Welcome back, guys. Here we are to gas laws, lesson 1, part 2. I want to finish off with our very first gas law. Now that we've talked about pressure and temperature, I want to start applying it a little bit. As we go through this, what we're going to do is learn about 5 different particular gas laws. Each one simplifies things about as much as it possibly can. And the first one we're looking at here is Boyle's law, looking at the date way back when, 1662, but he was really just looking at a relationship between pressure and volume of a gas. So what he did was state that as the volume of a gas changes, the pressure of the gas changes inversely. This is provided with one very serious set of conditions in which the amount of gas is fixed and constant, it cannot change, and the temperature is also not allowed to change. So this is kind of unrealistic, but if we simplify it down to just 2 variables, everything else is constant, it's very much like a lot of our experiments. What he found out was that pressure and volume are related inversely, which means that they behave oppositely. Take a look at this cylinder here. We have a certain amount of gas in a large volume of space. Now pressure, well, we talked about kilopascals and things like that, is easier to imagine if we think about what pressure actually is. It's pushes or pulls. For a gas, pressure is related to the amount of collisions that you would have with the side of the container. So, if I have gas molecules moving, and they are pushing on all sides of the container, including the plunger here and the bottom, and so on and so forth, there would be a certain number of gas particle collisions with the sides of the container per second. I hope that concept makes sense to you. Now, what would happen if I press on this plunger and decrease the volume to 1/2 the size? You still have the same amount of particles, you have the same temperature, which means the particles are moving with the same speed. Ask yourself, would this increase the amount of collisions with the side of the container per second? Or would they stay the same or decrease? So, same kinetic energy, same motion of particles, but a smaller space. What's going to happen is you're going to have way more collisions per second. And what we do is we measure that as pressure. So graphically, what ends up happening is as volume goes down, your pressure goes up because we get more collisions per second. So what that means is we have an equation that we can talk about. The pressure and volume product that you have in this relationship is equal to a constant value, which means it cannot change. So, if the pressure in your first situation times the volume in your first situation is manipulated, like it is here, and volume goes down, so volume 2 went down, how do you maintain the equality? Because it has to be a constant. Then the pressure has to go up. So we see that in the equation for Boyle's law. I know this is a lot of math, and I hate having to do this online through a camera to try and explain it to you. All right, but this is the nature of gas laws. We're looking at a lot of equalities, we're looking at a lot of relationships, and our first one here is showing an inverse relationship. The pressure volume of the first cylinder, number 1 here, must be equal to the pressure volume constant of the second cylinder. Your textbook shows this a little bit, but not really. So I'm doing a little bit of extra work just to talk about this constancy. Ultimately, because of all these things being at play, we can't really change things. As something increases, something has to decrease. That is our relationship. The Boyle's Law demo right here that we have will be a video that we can take a look at within this link. It is also in the gas laws section. It's just going to show you what happens as these particles are trapped in a container, much like my little arrows here, as they bounce around, and we're trying to contain them and look at what happens. All right. Really hope that makes some sense, but it's really just a mathematical equation. It is a ratio, it is an equality, it is a very simple thing to do in our calculator. So grab those calculators because we're going to need them for the next little bit as we get into our examples. All right, we're going to do the first couple examples in this lesson. I will save the rest for the next lesson. What we started off with in lesson 1 was just converting and looking at the different ways that we could express pressure. And so for this one here, what we want to do is just convert 90 kilopascals of pressure to atmospheres of pressure, a different way that we can do it. So 90 kilopascals, we want to convert this to atmospheres of pressure. This is no different than going between kilometers per hour and miles per hour, or pounds and kilograms. It's just a different way to express the same pressure, so the numbers will change a little bit. If we use the factor label method, which you may have seen in previous courses, it's really just using a set of fractions to move through. Any whole number is a fraction over 1, so that doesn't really need to go into the calculator. And what we're going to do is remember things from our rational expressions unit in math and some of the stuff we did in Science 10. We can use the position of the units to cancel them out and convert to other things. If you look at your data sheet or the previous set of notes, we realize that kilopascals are something I want to cancel out, and I'm trying to get to atmospheres. We talked about in a previous set of notes and on your data sheet about an equality. 1 atmosphere of pressure is equal to 101 kilopascals. So we can use these numbers to fill out our next fraction. Remember that 1 atmosphere is equal to 101 kilopascals. Now, if we were to do this and hit equals, kilopascals over themselves would cancel out of the problem. Take a moment, run this through your calculator, pause the video if you need to, it's all good, and what we get is 0.8910 atmospheres of pressure. All right, numerators multiply, denominators divide, we get this value. This is much easier than trying to memorize a bunch of formulas. The last thing we have to do, remember from our Science 10 review, is maintain our sig figs. We're only allowed 2. Leading zeros don't count. There's your 2 digits. The 1 rounds down. So 90 kilopascals is actually 0.89 atmospheres. Take a look at your data sheet. If 1 atmosphere was 101 kilopascals, then 90 kilopascals is less than this. Therefore, we are less than 1 atmosphere. Hope that makes some sense to you guys. I'm going to continue on the rest of the examples with the next part of the lesson. I'm trying to keep these little videos to 10 minutes or less because over 10 minutes, they tend to become problematic. I have a hard time uploading them, converting them, and all that other stuff. All right, so sorry for having to jump around from file to file, but so far this seems to be the best method to get you through the stuff, and I hope it's making sense so far. Any questions, email me, or alternatively, when we meet on Fridays in our video conference, ask me your questions then. Okay, see you in video 3.